Bohr model has given everything to explain the hydrogen spectrum. Let us recall the three postulates developed by Bohr. Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. From this postulate, we can conclude that each atom has certain definite stable states in which it can exist, and each of these possible states has definite total energy. We call these as stationary states of the atom. Bohr's second postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi, where h is the Planck's constant. Therefore, the angular momentum of the orbiting electron is quantized, and this defines the stable orbits. We say that L is equal to nh divided by 2 pi. The Bohr's third postulate states that when an electron makes a transition from one energy level to another, a photon is emitted whose energy is equal to the energy difference between the initial and final state. The frequency of the emitted photon is given by the relation h nu is equal to Ei minus Ef, where Ei and Ef are the energies of the initial and final states. Let us also recall the concept of energy level. The energy of an atom is the minimum when its electron is revolving in an orbit closer to the nucleus, and the energy is progressively larger in the outer orbits. The lowest state of the atom or the ground state is that of the lowest energy. At room temperature, most of the hydrogen atoms are in ground state, and when a hydrogen atom receives energy, the atom may acquire sufficient energy to raise the electron to the higher energy state. The atom is then said to be in an excited state. From these excited states, the electron can fall back to the state of lower energy with the emission of a photon. According to the third postulate of Bohr model, as an atom makes the transition from the higher energy state with quantum number Ni to the lower energy state with quantum number Nf, provided that the Nf is less than Ni, the difference of energy is carried away by a photon of frequency nu such that h nu is equal to Eni minus Enf. We have also studied that the total energy of the electron in the stationary state of the hydrogen atom can be obtained by En is equal to minus m times e to the power 4 divided by 8n square epsilon 0 square h square. Given the initial and final energy values, we can determine the difference in energy as h nu If is equal to Eni minus Enf, that is equal to m e to the power 4 divided by 8 epsilon 0 square h square times 1 by nf square minus 1 by ni square. Therefore, nu If is equal to m e raised to 4 divided by 8 epsilon 0 square h cube times 1 by nf square minus 1 by ni square. This equation is the Rydberg formula for the spectrum of hydrogen atom. The Rydberg constant is given by R is equal to m e raised to 4 8 epsilon 0 square h cube times c. Inserting the value of constants in this equation, the Rydberg constant value is 1.03 times 10 to the power 7 meter raised to minus 1. In this relation of Rydberg formula, if we take nf equal to 2 and ni equal to 3, 4, 5, etc., it reduces the equation for the Balmer series. The transition between different atomic levels result in light radiated in various discrete frequencies. As we have already mentioned, for hydrogen spectrum, the Balmer formula corresponds to nf equal to 2 and ni can have values from 3, 4, 5, etc. The conclusions from the Bohr model suggested the presence of other series of spectra for hydrogen atom, that is those corresponding to the transitions resulting from nf equal to 1 and ni equal to 2, 3, 4, etc. that is called the Lyman series, and nf equal to 3 and ni equal to 4, 5, 6, etc. that is known as Parskin series, and nf equal to 4, ni is equal to 5, 6, 7, etc. that is known as the bracket series, and so on. The electronic transitions corresponding to these series are shown in the figure. On the other hand, in hydrogen spectrum, each group of spectral lines correspond to electron transitions to any particular state. We can see that the Lyman series is in the ultraviolet region, the Balmer series is in the visible region of the hydrogen spectrum, and the Paschen and Brackett series are in the infrared region. The line spectra are sharp lines of definite wavelength. The various lines in the atomic spectra are produced as the electrons jump from higher energy state to a lower energy state along with the emission of photon. These spectral lines are called the emission lines. There are many possible electron transitions for each atom, and each transition has a specific energy difference. This collection of different transitions leading to different radiated wavelengths, making up an emission spectrum. Each element's emission spectrum is unique. We also know that when an atom absorbs a photon that has precisely the same energy needed by the electron to get excited to a higher energy state, the process is called the absorption. If photons with a continuous range of frequencies pass through a rarefied gas and on analyzing with a spectrometer, a series of dark spectral absorption lines will appear in the continuous spectrum. These dark lines indicate the frequencies that are absorbed by the atoms of the gas. The explanation of hydrogen atom spectrum provided by Bohr's model was a brilliant achievement, and this greatly stimulated progress towards the modern quantum theory. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.